So yeah, I think we can start. So for today, we'll be looking at what we call the Senpai. That's purely doing mathematical sort of expressions or equations. And in this case, our focus is going to be more on the symbolic aspect. So we are not going to be using um, the ordinary, sort of data types that we know, like the float, integer, and the rest. But rather, we are going to create them or remove them from ordinary Python objects into what we call symbolic objects. Um, let me be sure you are hearing me before we progress. So please, if you are hearing me, kindly show by hand so I know we are good. If you are hearing me, just a thumbs up would do. So okay, all right, okay, all right. So by Simpai, we are referring to just symbolic Python. And so we'll be looking at Simpai in detail. Now, if you want a detailed documentation, you'll go to the Simpai page, and that's the link indicated here. And then it has more detail on the Simpai and then some aspects of how to use it. And there's also a whole lot of, tutorial material out there to support. So the real question in here is, so why Simpai? Now we know Senpai is definitely free, and when you read from their documentation page, everything is written purely entirely on Python. It's Python based, so whatever you make use of within Senpai has its basic or its roots as purely Python. And so all you need to understand in order to use Senpai is a basic knowledge in Python. So if you are not so well versed with that, I believe the materials from day one, day two would be able to help. You can just go back to the GitHub page, check up on it again, and then try to go through. And that's good. And then there's also lightweight, and then this is virtually like a whole library. It has a whole lot of functionality. If you get to see how it works, I mean, you realize most of the things that we do are way simplified in this library. All right, they get way simplified in this library, and it makes life very comfortable. And in a way too, I mean, if you are lazy, let's put it that way, it makes solutions a bit easy. And so these are objectives. We would address some of them. In fact, initially I thought we were going to be able to address these numerical solutions, but for this particular lecture, I'm not going to include them, or for this training, I'm not going to include them. But then, if you still need it, I can send you some add-up materials, and then that would still be useful. All right. So as a way of introducing Senpai, what we need to do first is to import our Senpai, and this we've done from previous lectures. So the very first thing we do is to import the Senpai, and it's case sensitive, so we import Senpai as the standard name you see is SP. But then, in order not to be confused because of the SciPy we imported from our day 3 lecture, which we called SP, in this case I'm going to use the characters SMP. So for this particular training, when we call SMP, we are referring to Senpai. And so we can actually import our Senpai, and then over here we sort of initialize printing. That would allow the Senpai to sort of print the parameters or attributes in symbolic forms. But then we can still overlook this because in the interactive interface, which is for instance Jupyter Notebook, it will still work perfectly well, so we can skip this part. Alright, now the first thing to do when you are working with Senpai is you need to define your variables. And by the variables, now if for instance I type in here x, okay, I think I've already run this. Let me restart my kernel so that we see exactly what I'm trying to explain. So we import our Senpai first as SMP. Now the next thing is we just check the variable x. Now this will produce an error because x has not been assigned anything. Alright, and so this is just a normal Python variable which we can assign a value. So let me say x equals to say 0.1. Okay, or even let me use the string x. Now this is just a string x, so it writes it in the Python object format. But then the way symbolic Python thinks is that it deals with sort of mathematical symbols. All right, so if you are very familiar with LaTeX, you probably have been using maybe LaTeX for your presentations, your thesis write-up, and the rest, you would be so familiar with some of these symbols. So in order to generate that, we would use the Senpai symbolic creation method. And there are different ways of doing that. The very first one we will try is if I'm just trying to create one variable. Okay, so I'm going to use the keyword or the method symbol. Now bear in mind, this is just to create one symbol. So I have my Senpai imported, and then from Senpai I pick the symbol method, and that is with the uppercase S. And then I pass in here my variable as a string, which is x. So this x will be recreated from, it will be regenerated from a normal string, okay, to a symbolic character. And then we are assigning that to the variable x. So once we do that and we print out our x, you notice that there's a difference in the x that we get produced here, which is a symbol, than what we had if we had just printed a string. Okay, now if we check the type of this x, it tells us that this is a symbol created from the Senpai core subpackages. All right, and so we would always, for you to use Senpai effectively, you have to create your symbols. That's it's conc. All right, so there's one approach. Now the second approach is if I'm creating multiple variables or multiple symbols. For instance, I'm creating a and b. Now I need to use the method symbols, and symbols in this case would be started, I mean everything is just in lowercase, unlike the single one which is uppercase for symbol. Now symbols for multiple, all right, and we can recreate this in different forms. So now I pass in into sort of more like a tuple. Think of it as a tuple. I pass in these parameters, and then I just within the whole string case pass in my variables I'm assigning or trying to create the symbols from. So in this case you have a and b, right, and then I'm assigning them to the variables a and b. So if I print out a and b, I should see the symbols a and b. All right, if I print out just a, I should see the symbol a, and then same for b. All right, now there's one approach. The other approach is to just pass the symbols in as a list. Okay, and then as a list, every individual one will have its own item. So we have the first item of the list being one parameter, the next one as another parameter, and then we assign it to the variable. So this will still recreate the same a and b for us. Okay, so that's by way of creating the symbolic the symbols. Now what if we want to create, if we are doing this, say we need variables a0, a1, a2, a3. Now I only need to go back and then create from here, say a0 is this, a1 is that, a2 is that. So let's say sim.symbols, then I pass in here a let's say a0, a1, a2. I mean that's a lot. All right, and if I even decide to go and use the upper one, which is a symbol, and create them one after the other, that's way more lines means definitely you are going to waste more memory. So there's a more simplified way of doing that in Senpai. So if you remember the indexing we did, the indexing we looked at, and then also when we're dealing with the range, and we said you can actually use this to indicate the starting point or the starting counter, and then the ending point or the ending counter. So we can recreate that here. So let's say I want to create just x, 10 variables of x. So let's say we have x in here, and we call smp.symbols, and then I pass in the string x, and I tell it to start from say 0 all the way to 10. Now this is going to create x0, x1, x2. So if you've worked with vectors before, I mean in normal maths, you know how the vectors have individual indices or positions. So you have that same um, sort of symbolic items created for you. Now we can access any one of these parameters using the subset, and so I need the first one, so I call the zeroth item, and that would bring just the x naught. Okay, so if I do same for say x5, I expect to have x4. All right, and that's it. So we can assess individual aspects of it, and not just for one, but we can do a lot more. And think of it this way. So in this case, I'm going to have x, a series of x, and then a series of y created, and then we can see what the y values are, and that's exactly it. So we have x naught, x1, y naught, y1, y2, because x starts from 0 to the step before 2, and then y from 0 to the step before 3. Okay, now we can also, rather than using the tuple approach or the normal string method, we can still pass these ones in as a list. All right, and specify that, okay, x should be in the first part from 0 to 1, y should be from 0 to 2. Now what happens in here is that, let's see how the output of y looks. Okay, now this is treating it slightly different from the first. So the first one is purely, one dimensional. This appears as though it's a two-dimensional item. Okay, so if I pick the 0th item from y, in this case, it would produce just the first one, which was the x naught x1. And if I need just the first one, then I can probably add another 0 just to get the first item. Okay, and so that's one of the ways to think of the symbolic link creation. Now we can also, if I bring this, now when we were talking about the subsetting, array subsetting and the rest, we saw that if I have the first column, it's separating the initial and then the final, and then the second column will separate the end from the next one being the steps, right? But in this case, this is slightly different. Now we are going to, by this I mean I'm defining an x, all right, that starts from 0 in all cases, but then the first dimension should be 5 elements, the second dimension should be 2 elements. So think of it as a 5 by 2. Okay, so you have like 5 rows by 2 columns, and all of them, their position will start from 0. So once I create this, we have sort of series of x00, x01, x10, x11, x20, on and on till x40, x41. Okay, and so we can also use this to create sort of multi-dimensional symbolic variables. Okay, now what happens to the variables we create? We are not just creating the variables and that's all. We want to make use of them. So we can start off with some expressions. And like I said, so let's say in this case, all you need is a basic understanding of Python. So we have this 2x squared plus 3x plus 5. And so in Python, we would have written this as 2 star x star star 2. All right, this is 2x squared. If I run this, okay, I think we regenerated our x. So let me use, because our x here, okay, the x here has now become a tuple because of the final x we created. Okay, so let me just create one item for x. So we have x being smp.symbol of x. All right, so we have just one item for x, and that's what we want to use. Okay, so now we have 2x squared plus 3x plus 5. So 2 times x star star 2, that means 2x squared, and it shows it as such. And then we have plus 3x, so let's see, plus 3 star x. Don't forget the star is the multiplier, so it's, you can't just write the 3x without bringing the asterisk, otherwise it's treated as an error, coding. So this gives us 2x squared plus 3x, and then we can add our 5, and then we have our 2x squared plus 3x plus 5, and we can do a lot more with this. Okay, so we want to build on it gradually, so we can express all these symbolic links as expressions and all that. Okay, so we have that, and then there's another example here which we can try our hands on. We have 8x cubed minus 6x squared plus 16x plus 289. So 8 star x star star 3, that's 8x cubed, minus 6 star x star star 2, that's 6x squared, plus 16 star x, which is 16x, plus 289, and that creates an expression of that format. Okay, Now let's look at this. We want to have square root of x. We've created our x, but then when we raise this to the power 1 over 2, we are getting x to the power 0.5. Okay, but this is slightly different. This is not the same as what we are having here. In most cases, this approach would be giving us sort of an approximate value because it's using a numerical solution. I mean, it's solving it as a numeric, okay? Not necessarily a numerical solution as in numerical analysis. Think of it as it's dealing with this as a numeric based on the Python numerics. Now we have 1 divided by 2, okay? So that is definitely going to give us 0.5. And so now it raises x to the power 0.5. Let's bring this one here. Let's say we have 1 over 3. Now you notice that this has given us sort of an approximate value. But this is not the same as we having the cube root of x. If I want x to be to the power 1 over 3, okay, now I need sort of an exact solution. Now this is only dependent on the number of sort of visible points or floating points that's allowed by the system. Alright, so that's where there's a bit of issue. So what we would need to do then is to now bring on board some data variables or some data types which Senpai understands. And so the two we can think of are integer and then rational method. Okay, so we start off with the integer. Now I want this to appear exactly as the square root of x. So what I need to do is to pass the fractions that we had into the smp.integer method. So I pass 1 into an smp.integer. That means it should treat this one as a symbolic Python integer and then also treat the 2 as a symbolic Python integer. And then when it's done, it should find the division of the 2 and then raise x to that power, and that gives us exactly our square root. Okay, because Senpai is built to understand. Once you are dealing with symbols, whenever it comes to symbols, it's built to understand. The moment you start using Python objects, that's where you might have some issues. Okay, now we don't need to always do for all the 2. Once I've done for 1, once we've sort of converted any one of them, be it a numerator or denominator, to an integer, it will still work perfectly. Alright, so any of them, we are good to go. As long as one is okay, one is done right, that's okay. Right. Now let's say we have the same square root of x, which we are raising to a power of 1 over 6. So we are expecting to have x to the power 1 over 2 times 1 over 6, which is like x to the power 1 over 12. Now the moment we do this, we have our x raised to the power 1 over 2, which is exactly what the first aspect gave us, which was the square root of x. But then in raising this to the power 1 over 6, I went back to use the same Python object. And you can see it tries to evaluate it here, and then it gives us an approximate value. Alright, and so we have this. Now let's say I want to raise this again to a power of 12, and let's see what happens. Now I'm expecting that what we're having as, okay, no, let me put this in parentheses, otherwise we might be getting exactly wrong outputs. Okay, so well, this one worked, but then in some cases what you do is when you look at it, when you look at the output, it would bring you back to sort of extra floating points. Okay, you would be getting, instead of having the exact value, you'll be having extra floating points. So that's why you wouldn't want to treat them as ordinary Python objects, but rather you want to deal with them as as symbolic Python sort of symbols. Right, so it means we would have to convert one of these at least into an integer symbol. So we can then pass on here smp.integer and then change any one of them to a symbolic integer, and then that should work. Now the moment we divide an integer, sort of a symbolic item, or we perform any arithmetic on a symbolic item and then a Python regular object, we will be having an output of a symbolic object, or a symbolic we'll have a symbolic variable. Okay, so that's why we can just set for one and not think of the second one, and we know that should work because they are being evaluated together, right? And that gives us the 12th, root of x, which is our output. All right, and so there's some extra example telling us how we can use the integer method and so on. Okay, and some extras again here. Once you get the approach, it's easy to try your hands on all these examples and then see how it works. All right, now we can use the alternative approach, which is where we are going to use the rational. Now, rather than specifying them, for instance, in this case where we had integer for 1, integer for 6, and if they are multiples, then it's going to be a whole range. I can just make use of the rational method, and then what we are saying is that now let's say we have this x, all right, and then think of the rational as this. So we have smp dot rational, and then we pass in 1 and say 2. I believe you get it. So that gives us sort of a fractional aspect, and this is treated as a symbol. So if we find the type, the data type of this, you'll notice that it's evaluated or created from the Senpai core. All right, it tells us this, how we can change this into any other parameter. It tells us this rational. All right, okay, and once we are doing that, then it means we can simply have our x raised to a power of a rational item, and that should still give us exactly what we need. For instance, in this case, the fifth root of x, and then we have our output right. So if I needed, in this case, for instance, the 12th root, I could just pass in here the 12, and then we are good to go. Right, now what if I pass in here to say 24? Let's see what the output would be. Okay, so you notice that the Senpai gets to understand exactly what you are dealing with, because this rational is supposed to create a fraction, and so it would evaluate that fraction for us before it would raise it to the power. So it's very simple to use this rational method and all that. Okay, and if for instance we had, in the first case, we had 1 2, which was the square root, and then we wanted to multiply that, or wanted to raise that also to another power of 1/6 or 1 over 6. Now bear in mind that you need to be clear on where the parentheses are. If I bring on board here star star smp dot rational and then pass in 1 over 6, it means, bear in mind, Python uses the PEMDAS approach, so it's going to find the exponential form, and it starts from the right to left. So there's an exponential here, there's an exponential here. So this rational value we are having would be raised to the power this rational value first before the x is raised to the power of the final output. And so even though we want x to the power 12, that's not how it's going to be treated. We're rather going to have 1 over 2. You're going to have something as this. You have like a 1 over 2. Okay, that 1 over 2 would be raised to a power 1 over 6. And then whatever we get from this evaluation, that's what x will be raised to the power. Okay, so even though we want x to the power 12, we'll be getting something totally different here because we failed to pass in the right parenthesis. So I know, okay, I'm going to make x raised to the power 1 over 2. Okay, so I separate that in its own parenthesis, and then I raise the whole output to a power of 1/6, and then that should give us a 12th root again of the x. All right, so that's the beauty of generating the Senpai data types using the integer or the rational method. And there's still some more examples for you to maybe try your hands on and then get to see how it works, and some extra detail. Also, there are certain special symbols that you want to create in Senpai, and it's like it has its own default way of being called. So in Senpai, if I want to make use of the pi symbol, I just call the SMP or the Senpai and then call the sub package of pi, okay, from it. Now let's say I import my numpy here just to produce this pi value, or sort of try to evaluate this pi value. Okay, so I make use of the float method, and then it tells me what the pi value is, 3.14, that in that order. But bear in mind, this approach will be soon deprecated because there's a very simple way of doing that in Simpai. Okay, so for instance, I have my uh, I'm sure we'll be looking at it in a bit, but let's see, smp.pi, and then let's try this. Okay, this still gives us simple. Okay, I think we'll come back to it. We'll be looking at it again. There are a whole lot of items listed in there, so just so I don't get all those information jump up in my head. Okay, so you can still bring on board, NumPy, any of the extra packages, and still work on the Simpai symbolic objects with those integrations from regular Python, and that will still work exactly well, right? And so we have, for instance, the square roots. We can make use of smp.sqrt of x. That will just produce the square root of x for us. Okay, and like we said, we can equally use the rational method just to regenerate this. And then if I want this e, the exponential symbol, then I can make use of smp dot an uppercase of e. This is 1, and then we can also make use of smp dot exp. That's the exponential. All right, but this produces exp right here. But for instance, if I sorry, if I were to raise this e to a power, let's say e to the power 2, then if I call this as sort of as a method, that should be treated as such. Okay, but then the moment I'm not dealing with it as an e that raises, I mean raising that exponent to a certain item of a power, it will just print out the exp. And so we would want to make use of the uppercase of e just to get this symbol as a symbol on its own. And then in the case where we want to sort of use that in an expression, then we can make use of the exp, and that still works. And either ways, you can still even use the smp.e, and in this case, say raise it to a power 2, and you have the same output. Okay. And then also we have the trig function. So we have the cosine, the sine, and then also the tangent. So we have, for instance, smp.cos of an angle or something. So smp.cos of x will produce sine x. Smp of sine x will produce, I mean, smp.cos of x will produce the cos x. smp.sine of x will produce the sine x. And then smp.tan x will produce the tan x, right? And then, I mean, it's built to arrange itself, or sort of align itself in known sort of trig approaches. So that's it, and that's what we have. So we have our sine x plus the cos x minus the tangent of x. Okay, and then what if we would want to have, say, a cos squared of x or a sine squared of x? All right, then we can bring on board our smp.sine of x and then raise that to a power. And raising the whole sine of x squared is the same as having a sine squared x. Right, and so that's how we can treat this one too. And then we can also use Simpai for simplification. So let's say we have this equation which is 3x plus 5x, okay, plus 20 minus 30. Now 3x plus 5x should produce 8x, and then 20 minus 30 should produce negative 10. So if we have these ones, and when we just run the equation, Simpai would just simplify it by default, okay, and give us a simplified value. Right, and then we can check the data type of EQ1. It tells us this from the. Any question, please?
I didn't get the aspects where you brought the course first, but when you run the program, or you brought sine
I
first, but
brought
when
the
you
course
wrote,
first.
no, you brought course first.
Hmm.
But when you run the program, sine came before the course and the tan.
Okay, so what's the name? Simpai has its own structure of laying out these sort of trig functions and even some other outputs. Okay, the same way when you have, for instance, a cosine and then an exponential function, it would arrange it in its own way, bringing sometimes the exponential first before the cosine. But then it doesn't necessarily affect your output, right? Your output will still be exactly the same. I mean, and sort of all these additions are sort of, I'll say commutative. Sine x plus cos x is the same as cos x plus sine x, all right? So there's nothing really lost here. I don't know if you get it. Yeah, sure. Okay, so when we find the type of the simplified equation, it tells us there's actually an addition that was generated from the Senpai core. All right. Now let's look at this other example. We have 4x plus 5 plus 3x squared plus 4x minus 7. All right, and they are all in their individual parentheses, but we are adding them because of this addition symbol. It's going to simplify them. So we are going to have everything added up, and then in the end we have our 3x squared, 4x, and then 4x giving us 8x, and then 5 and then negative 7 giving us negative 2. All right, so we run that and then it gives us a simplified output. But what if this were to be a distributive property, not commutative? We are not adding, we are just multiplying. In this case, for instance, we have x times into bracket 2x plus 2. Now this would give us the same x into bracket 2x plus 2 because one, it doesn't know exactly what you want the output to be, whether it should be expanded, whether it should solve for some roots and all that. Okay, so it will just leave it in this default form. But then there are ways you can treat it explicitly and tell it, okay, maybe I need an expansion, so expand this for me. All right, and then it will do that. I can tell it to simplify it, and then it would put it in a more simplified form. And that's by way of, I mean, the simplification or trying to simplify your Senpai expressions. Um, so that it doesn't seem we are racing. If there's any question, maybe I would take it now, address them before we move on to the other aspects. So please, any questions? If there are any questions, you can type them in the chat or you can move to the top of the class where the podium is and then kindly ask. All right, so we can also do some, simplistic factorizations and then expansions. Okay, and the beauty of Simpai is that it's cross range in terms of the ability to perform mathematical operations. Right, it starts from the very fundamental math to the expansive cases of mathematics you can think of. Right, you can use them for quantum solutions, and then, I mean, dealing with quantum physics, quantum, all the various types of quantums, and then even beyond the components of the limited mathematics you can think of. So it can be used for a whole lot of things. All right. Okay, so let's say with the expression we had up here. Okay, no, there's actually a different expression. So we have 8x cubed. So let's call this one out. So we print our y so we can see what y is. Y is 8x cubed minus 6x squared plus 16x plus 8. Now we can bring on board here our SMP dot factor if you want to factorize this. All right. Sorry, I need to pass in the y so that it factors is going to factorize the y. Okay. So in this case, I called the Senpai and then called the sub package factor to factorize, and I told it which equation to factorize or which variable to factorize. So it picks this variable and then factorizes it. All right. Now this is one approach. The second approach is we can also just simply call our y, which is the equation we had, okay, and we can just call our y dot factor, and that should still work. So the expression we are having here dot factor, and then we open and close the brackets for the method, and that will still generate the factorized output for us. Okay, and that's exactly what we've explained here. Now let's take this one. So this is more like a quadratic expression. I want to sort of factorize them. So once there's something we've also before, we expect that we'll be having, I mean, a 1 and then a 6, right? That's like 6 and then negative 1. And then when we solve, we should have like negative 6 and then 1, I believe. Yeah. So now I write the expression first. So my y is a squared. So I think we probably defined a somewhere. above. Let's check. If not, we'll have to create the symbol. So we have in here a. Alright, so we already have created the symbol a, so we can go ahead. So we have y being equated to a squared plus 5a minus 6. And then the expression we are having, which is the y, which looks exactly like what we have in the question, which is this. We tend to factorize that, so we have our y dot factor, and then that's all. Now you notice in this case we don't pass anything here because what we are factorizing is what we've called out here, the expression. But if I'm going to bring the factor from the Simpai, which is the SMP, then I need to tell it which parameter to factorize. That's when then I'll pass in the variable for the equation into the factor method. Alright, and then we still have the same expression. And we can also expand, just as we did a factorization with the factor, we can also use expand. So let's say we have this a minus 1, a plus 6. We want to take it back to this aspect. So we have the a minus 1 times a plus 6, which is, okay, so which is the expression here. And then we are saying that this whole expression should be expanded. Right. So we have a minus 1 times a plus 6. When we expand, we get our a squared plus 5a minus 6, which is exactly as the equation we have up here. What if we want to solve this? Probably want to pass in, want to substitute a value in here. So let's say maybe 3. We can just add the method dot subs, which is to substitute, and we tell it what we want to substitute. So we want to replace, for instance, a with the value 2, right? And this would evaluate it. So we have 2 in here, so there's like 2 squared, which is 4, plus 2 times 5, which is 10. So that's 14 minus 6, that's 8, giving us the value 8. What if I decide to replace this with, now I'm going to pass in a regular Python variable, say y squared. Okay, we are going to pass in here y squared. So wherever there's a, it should be replaced with y squared as a string. So once we do that, it does the replacement for us. Okay, and not just that, but we can also even pass in a symbolic link again. So let's say, I don't know if we've already created a variable for y. Okay, no, we've already overwritten it. So let's see if z is there. No. Okay, so we can still create a new variable. So let's say we create the variable y to be equal to smp.symbol, just for one symbol, and we pass in here our y. So then we can just call this symbolic item, okay, without the single quotes. Otherwise, it will become a Python string. But then in this case, this y is the symbol. So we pass it in, and then we get the same y squared plus 5y minus 6, wherever the a has been replaced with y. Okay, all right. So we can do that method of substitution. In this case, you are replacing a by 5, and then after expanding, we get the value. Okay, and then again, we can also replace with other, like we already said, other string types and all that. All right. I also said we can also substitute in a defined symbol. So based on the symbol you are having, which is in this case the y we define, we can pass that y in. Now, let's say we had, let's take this to be our y again, which is um, the same as the question. So let me redefine that. So we have y being, so we have y being the same question, and then we pick. Alright, so let's see the y again. So we have y being the expression here, and then okay, I wanted to just expand first. Okay, so let me pass this back. So let's say we are going to expand this and then replace our y in. So I have this expansion. I can substitute the a in there with my y. And then after it's brought it to this point, it passes the y values back in there. And then we can have the detailed expression, right? And it sort of simplifies it out, okay? So we have a squared being the y squared component with this whole items passed in there, and then the 5a being 5 times the whole y component passed in there minus 6, which has been then evaluated for us and simplified. Okay, right. Yeah, I think this is the same example. Here we just created multiple symbols and we picked one particular symbol to represent or to replace the a parameter in there. Okay. And it's quite the same example in here where we are using a string as replacement. Okay, so once you understand one, it's very easy to follow through the others. All right, and the substitution method works anywhere where you can just pass a value into an expression, into an equation, and it works. All right, so we have this example here. It says set an expression for the following, that's x squared plus 2x minus 5, and then evaluate the expression of x equals to 1.5. So we have to write this as expression first and then pass in a substitute of 1.5 being x. It says also make a variable substitution z for x. So we have to create in another sense, create a variable x or a symbol z to replace the x. Alright, and then we have to do the same thing for x being y squared. Alright, so we have our expression which is the x squared plus 2x minus 5 as shown. And then we can then substitute x by 1.5 and we evaluate that, and that gives us 0.25. Okay, now bear in mind when we check using a Boolean approach, we check this evaluated value or the variable here, we compare it to the float of 0.25. It tells us this is true. Now it is true because the magnitudes are the same, the values are the same, but then they have different data types, so comparatively they are not the same in terms of properties. They're only the same by magnitude in terms of the value. Okay, now if we check the data type of the evaluated variable as again 0.25, this produces a false because the type of 0.25 will give us a float, but the type of eval1 should give us a float that is deduced from symbolic Python. Alright, so once we look at this from here, it tells us there's a float that was generated from a symbol or a symbolic Python application. So the two are not the same in terms of their properties, but then in terms of magnitude, they are similar because they produce the same value. Alright, and then in the second aspect, we're supposed to substitute x for z. So we can either create a symbol z and then pass the z in, or we can just replace x by a string of z, and that works. And that's the same for, okay, so this is the other approach where we created a symbol and then passed that in, and it still worked. And then the other one, which was x, replacing x by y squared, we can pass in x to be equal to y squared, and then this should work. Or we can create a symbol for y and then pass the y squared in there. Alright, and there's also another example. So once we understand the first one, it's quite similar here. We can create this expansion of such a polynomial too. Alright, and yes, so based on the knowledge we have, we can expand, we can factorize, and we are good to go. And I've already explained the exponential and how it applied as in line with the uppercase E. Alright, and so we are good. And then also we can produce equations and solve equations in Senpai. Very simple. Okay, so what we need to generate the equation is using the keyword or the method EQ, which is to generate the equation. We can also use solve set to solve the equation. We can also use linsolve to solve linear equations. And then we can use just the method solve to solve all equation types. Let me use many yeah, to be on the safer side. Okay, so the solve can just be used to solve different equations of different types. Solve set will also, solve the equation but produce the output in the form of a set. Okay, the solve will just produce an output of a list, And then the lin solve is purely for solving linear equations. So let's say we have this expression, or this equation. In this case, we are equating it to 0. So there's an equation. We have x squared minus 5 equal to 0. Now, to create this equation, we have to call our SMP, which is the Senpai, dot EQ. Like we indicated, we are generating the equation. Now, the first item, okay, should be the left hand side of the equation. The second should be the right hand side of the equation. So in this case, we have x squared minus 5 on the left hand side, and we have 0 on the right hand side. So if we run this, okay, I use an uppercase x, it should be lowercase x. So if we run this, we should get the expression x squared minus 5 equals to 0, which is exactly what we are having there. And then we can solve this. Alright, so purely we have this in here, p equals to the same thing, and then we call the variable p, which contains the equation we've created. Now, in the very olden type of Senpai, if I don't specify the right hand side, by default it will take it to be 0. Okay, but then this is quite deprecated, it's soon getting obsolete. So if we just try that approach, in the first instance, for instance, in my case, I had this error showing, and then multiple instances it wasn't showing, but then it's only telling you that this will soon, in some time to come, not be existent, it will be non-existent. So it is necessary to specify always the left hand side and the right hand side of the equation. So for instance, if I have the right hand side being another expression of x, so let's say x plus 2, then I need to specify it as such, and then it will produce the equation for me. Alright, and then we can solve it using the smp.solve, and we pass the equation we generated in here. So let's see the equation again. We have p being x squared minus 5. Okay, the equation has changed in this case. So we're having x squared minus 5 equals to x plus 2. Now this is typically the same as x squared minus x and then minus 7. So x squared minus x minus 7 equals to 0. So if we solve this, it should give us the solution for this expression. And it tells us the first hand side is 1 over 2 minus the square root of 29 over 2. And then the second hand is 1 over 2 plus square root of 29 over 2. Alright, now let's use something that is quite relatable. So let's say we have smp.solve, and we are solving this expression. So let's call the equation in here. So we have the equation being smp.eq, and then we have here, say, x plus 2 equals to 0. So we expect this to produce negative 2. Right, and that's it. We are good to go. Alright, now if I decide to use, you notice that this produced a list for us. So if I check the type of this output, it tells me there's a list. Now if I decide to use the solve set, it produces the output as a set from the Senpai, and then you can see how the output looks. Okay, so this is actually a set, because of the curly brackets which we saw from lecture 1. Okay, so we can use the solve set and then the solve to produce the output of this equation and multiple equations. All right, so there are some others for you to try your hands on just to get familiar with it. So in this case, we have we have 2x plus 4x plus 4 equals to 0. So 2x plus 4x should give us 6x plus 4. So 6x equals to negative 4. We have x being negative 2 over 3. And that's exactly the solution we have in here. Okay, and that gives us the answer. And we can again use the solve set for that approach. Now what if I have two separate equations, and more like a linear equation, and I'm trying to solve it, or think of it as a simultaneous equation which I'm trying to solve. Okay, so in this case we've created x variables, which is x1 and x2, and there's y1 and y2. Okay, and then we are saying that the first equation is the first value of x, okay, which is in this case the x1 plus 5x2 should be equal to the x, the third item. Okay, so let's produce this one first so that we see how the output looks like in the first instance. So we have the symbols created, which is x1, x2, and then y1, y2. And all these are assigned to the variable x. So x0 is the first item, x1 the second, x2, and then x3. So now this is quite relatable. So we have in here SMP dot equation x0, which is now what we are having as x1 here. The zeroth item is x1 plus 5x2 being equal to y1. And so this is how this expression or this equation would read if we had to equate out. Says x1 plus 5x squared, x1 plus 5x2 equals to y1. And the same way, if we bring in the second equation, we expect that it would give us the output of that equation. So if we type in EQ2, we notice that x1, which is the zeroth item, equals to the 5x2 minus y1. So we are going to solve this equation, this set of equations sort of simultaneously. So then we make use of the lin solve, all right? And the lin solve approach demands that we pass the equations we are solving, all right? We are solving linearly. We are going to pass the equations into the first hand side of the parameter, which is what we call the system. And then we now define the symbols that we want to evaluate over here. Okay, so we have the equation 1 and equation 2 passed in here as a tuple. And then the variables we want to evaluate being x0, x1, x2. And then we can produce the result, and it tells us, okay, the first item is x0 is evaluated to 0, x1 is y1 over 5, x2 is y1. And I believe if we just specify which parameters we want, it would also produce just those parameters. Okay, so depending on which ones you want, you can equally specify which variables or which symbols you want to produce the outputs for. Okay, and then that's it. And so we also have another example here which we can use to solve the roots. I've already explained this, so quite straightforward. I think you can just use the solve method. We create the equation, we use the solve method or the solve set, and we are good to go. And then also we've seen one example of simultaneous equations, so we can do same here, trying to solve these three equations simultaneously or using the symbolic approach. So we create the equations and then we solve them as such. Okay, all right. Now if we're supposed to be solving this using the default SciPy approach, this is how the method would be. Now we've only built this as a function, so it means in the SciPy approach would have assigned the parameters to their respective variables and then define the expressions, and then we return the expressions. So when we return the expressions, now in SciPy there's the f solve, which will allow us solve the f's, which is the system, what we are calling the system. So allow us solve the system, all right? So because that's what be going to be outputted. So the f here refers to the function name which we are calling. So once we call the function name, it's going to produce all these outputs, and then we evaluate them over these parameters, and then it solves for us. Okay, and that's similar to the approach we used in here for the second one. All right. If there's any question, I'll take it. If not, then we can also look at some differentiation integration, and then probably that'll be it for today's session. Alright, so since there are no questions, I would go ahead. So for a typical differentiation, you are thinking of maybe differentiating an equation or an expression with respect to something. So let's say we have df dx, right? So we are going to call this maybe a dy dx. So we create a symbolic link, or the symbolic variable or parameter, which is x. And then we create the equation for y being x squared. So we have the expression y being x squared. So y is just x squared. I want to differentiate this with respect to x. Now if I differentiate this and I don't specify, because it's only x as a parameter in here, it will differentiate with respect to x. So differentiating this with respect to s, we expect to have 2x. So the SMP.diff of y will produce the differential or the derivative, which is just 2x. Now let's say we have y being 5x squared plus 6x minus 15. We expect to have 10x plus 6. Okay, so once we get our expressions right, we can differentiate our y, okay, with respect to x. Bear in mind, if I don't produce the respect with respect to aspect or what I'm differentiating with respect to, it would pick, because it's just a single parameter, it will still use that same parameter. Okay, but then to be on the safer side, you can specify so that it knows I'm differentiating y with respect to x. And then let's say we have this cos squared x, then exponent, the e to the power of x. Alright, and we are creating this. Now we have smp.cos x squared, which is the cos squared of x, times the smp dot the exponential of x. Now we notice again from here, based on the question Adam was asking, even though we had the cos before the exponential, by Senpai's approach, it arranges the exponential first before the cosine. Alright, and then if you are to evaluate this, we know what our y is. When we find the differential, we know definitely it's going to hold one, um, differentiate this whole item first, and then when it's done, it would add it up to holding the other component and then differentiating the other one. And so once we differentiate our y with respect to x, and both the exponential and then the cosine or the trig function both contain x, we expect to have the output, right? Which when you solve, definitely you would realize it comes back to the same expression. You get the same output. So you can try it out, maybe try to solve it also, and then be sure that it's working well. Right. And once we solve, we can also substitute. So let's say we are substituting x with a value of 3. We can substitute x in here and then we get the output. Now once we have this output, we can also simplify. Okay, so we can again simplify to produce a more simplified result. And so this will sort of simplify everything. What it did was to bring the um, exponent 3 out and then sort of keep the others in by just solving them using the trig solutions. All right. And then we have this. Now our function is dependent on x and y. So we have created the symbols x and y, okay, using the tuple approach. And then we create our expression, our equation, which is x times y exponent xy, which is what we have there. So we check our f, which is a function, and it contains exactly that. Now I want to differentiate with respect to both x and y, like the question is saying. So we are finding the derivative of f with respect to x and y. So in one way you can think of this as, okay, when I get my f, I can have f dot diff and differentiate this with respect to x, which will produce the output with respect to x alone. And then when I get the output, I find the derivative with respect to y, and that gives me, I mean, the expression we are having up there. So differentiating x and y. Now that is true, but then we can also simply just have our f and differentiate with respect to x and y in the same line. So in this case, we have f dot diff, and then we pass in here x and y. Okay, and it understands I have to differentiate x and y together. Now this is more simplified an output, so we can again expand this output to be sure that we are having the same as the top one. Okay, and clearly we can see it's the same result. Okay, okay, so that's the expansion down there, and I've already explained how to do this. That's the same as defining the derivative of x alone and then later the derivative of y. Now what if I'm using the smp.diff? I'm calling the diff from the smp, not just attaching it to the expression or equation we had. I call my smp.diff, and then first I'll pass in the equation, alright, or the expression, and then comma, I indicate what I'm differentiating with respect to. So in that same order, so with y and then with x, right? That means differentiate f with respect to x and then also y, and then we have the same output. Again, when we expand that, we should get the same result. Okay, so there are some examples we can still try our hands on. So we can still simply just do with respect to x, with respect to y alone, and then some questions for us to try and answer. And then when you get the derivative, you just substitute the x with the value 3.3, and then you see what the solution is, right? And like I said, in this case, the exponential, we can use the smp.exp because it's raised to a power 2x, okay? Or we can just use the smp.e and raise that whole thing to a power 2x, and that should work the same way, and we should have the same output. Okay, so that's how the differentiation works. Simply, you would make mention of your smp.diff for the derivative, and then you pass in here the equation and then the variable you are differentiating with respect to. So if there are multiple variables, you can set the order, maybe variable 1 and then variable 2 and then variable 3 in that order. And that's how simply the derivative or the differential works in here. And once you are dealing with calculus, when we deal with differentiation, we can also deal with integration. There's way more that Simpai can do, but for time's sake, we wouldn't be able to look at everything. There's only to get you aware and then be sure that at least you know the basics, and then you can then build on it personally. So to integrate, we just make use of the integrate method in Simpai. So you have our smp.integrate, and then for instance in this case we are integrating x squared with respect to x. So we pass in our equation again, which is x to the power 2, and then we tell this to integrate this with respect to x. So by integrating, we know this is going to add 1 up here and divide by the total we get up there. So we are going to have x cubed over 3. So once we integrate this, we should have exactly the x cubed over 3. And then the same way we have a cosine squared of x dx. So we create our equation, which is the smp.cos of x squared, and that gives us the cos squared of x. Alright, and once we have the cos squared of x, we can simply integrate this. So we can call the smp.integrate method, alright, or once we have the expression or the equation, we can just pick the equation. For instance, in this case, we could have just picked this equation, which is the x squared. Could have just picked this expression of this equation and say, okay, dot integrate, and then tell it to integrate with respect to x, and it should still work the same way. Alright, so once we create our equation, we can just pick our equation dot integrate and indicate which variable to integrate with respect to, and that gives us our integral output. And alternatively, we can just use the smp.integrate and pass in the equation followed by the variable to integrate with respect to, and we'll still have the same output. And once you are done with integrals, you can also deal with integrals that have bounds, so the lower and upper limits. So in this case, let's say we have this equation or this expression x squared plus 4x, and we are integrating with respect to dx. Okay, we are integrating, sorry, with respect to x, and our limits have been provided as 0 and then 5. So all we do is to first define our equation or the expression, which is the x squared plus 4x, and then we are going to integrate the equation with respect to x. Now bear in mind, we had this. If I pass just the s here, this will produce the integral without the bounds being applied. Okay, so this just gives us the output of this integral. And then now we decide to, in place of passing just the variable, we are going to tell it, okay, I want you to create this with respect to this variable, but then the output should be computed within these bounds. That's for 0 to 5. Okay, so evaluate the output of the integral at 0, evaluate it also at 5, and then find the difference between the 5 and then the 0 output that's evaluated, and that would give us the overall solution. So the total integral within these bounds. Okay, and we can do same with this. We have an integral of cos squared x, which starts from negative pi over 2 all the way to pi over 2. So all we do is to first build our expression. So we've already defined our x. That's why when we check x, x has a symbolic outlook. So we've already had defined our x. So we can define our equation. Let's say equation 1 is equal to SMP dot cos, and then we pass in the cos x squared. So there's our equation 1. Okay, so we have our cos squared of x. And then we tell this to find the integral. So SMP dot integrate, or let's stick to the easy option. We can just have EQ1 dot integrate. Okay, and we can integrate this just with respect to x, which is good. All right, but this time we are passing in the bounds, so we are not just passing in the x, but we are telling it integrate this with respect to x from negative SMP dot pi all the way to SMP dot pi, and that gives us the output. Okay, this will give us pi. Okay, I think I saw something else. The question says pi on 2, so negative SMP dot pi over 2, and then the same as this SMP dot pi over 2, right? And this should still give us the same output, right? So we are going to have pi on 2 as the output of this integral within this bound, right? And that's the output, and we can simply just equate it as such, which is what we're having down there. All right, so we kept here also another example for you to try your hands on. First, we have our x squared, we have also our sine x squared, and we are integrating this with respect to x within these bounds. So you can just simply see how the equation is created and how we integrate within the bounds, and then the output we get. All right, and if there's any question, I would take it. If not, this is where we would be ending the fifth session. So please let's ask questions. All right, so this is where we'll end the session. It's been 5 great days of learning Python, and then I look forward to see how you'll be applying it, and then purely exactly what you've learned, see how you apply it in your various fields of work. And we'd like to say a big thank you to you for joining in, and I'm glad that you stayed till the end. All right, so maybe we might take the group photo if there are no questions. Yes,
Hello.
yes, Adam, please go ahead.
Yeah, I want to know like at the part where you just write the equation, maybe equation.
Mhm.
This is sometimes maybe if you are writing like your presentation, sometimes you have to write equation for them to understand what you're about to do. So I want to know whether after writing that equation and you mark down that cell, will it still display as it's supposed to display?
Okay, so I mean, as a symbolic Python, when you create it, when you write it, you are writing within this cell as a code. So when you look up here, it is as a code. If I change this to a markdown, it's not going to be treated as a Python sort of Senpai approach. All right. Now it's different. If I want to create those symbols or those equations, then it means I can apply LaTeX sort of formatting. So for instance,
Uh,
this is
okay.
something that's probably outside the scope of what we are doing as Python. That's why I didn't bring it. So you notice most of the equations I kept in here were like that. So for instance, I have this dollar sign, and within this, so let's say I'm just passing in, uh, let's see, maybe a fraction. So I can just pass in this fraction and then indicate the lower and then the upper part. So maybe in the lower
Okay.
part, passing x, upper part, passing maybe 2, this x over 2. And so that is it. All right. And then if I want it to be centered, then I just use a double dollar sign so that it gets to center this for me. You
Okay.
get it. So that's purely,
Yeah, yeah,
it's not really Python. That's more of an application of, say, LaTeX formatting and the rest. Yeah.
yeah. We know that thing. That was the type of assignment and all that stuff.
Oh, okay. All right. Then at least once you have it, then it's very easy to also apply that within the Markdown and then, create something that's very easy to share and then make it presentable.
Okay. Thank you.
All right, so Melvin, duly noted. Yes, if there are any other questions, I'll address them. Yes,
Hello.
Oga Ajayi, please go ahead. But I think your microphone is very low.
Okay.
I don't know if you can speak louder a bit.
Is it better now? Can you
Uh,
hear me now?
yes, I think we are okay. This is good.
Better now.
Yes.
Okay. First of all, thank you for giving us opportunity to be part of it. And towards the end, I think I started enjoying it because, like I tell you, I'm more of the engineering, and I use first plan a lot. So I guess I understand. I now feel the this looks simpler and much more easier to manage,
Mm-hmm.
like in the first class environment. So thank you for giving us the opportunity. The other thing that I would like is after this session, because there are other questions that for now I was able to go over the first class and second class.
Mm-hmm.
In fact, it will be in the third class, and sometimes you say I need to go back to first class because I downloaded the sessions.
Okay.
But there are some questions that you want to ask, and then they are not outside. Of course, I have a way of communicating with you. But what about others that in this group? Do they also have a way of getting back to you to say, okay, we have these challenges. Can we discuss it outside this group? Are there
Okay.
ways we can get back to the team? So that like we said, we can always so we can expand the scope, not so that we continue to interact
Okay.
after
All
this
right.
session.
Okay.
Thank you.
Sure. Duly noted, Mr. Jai. So just a quick one. I wanted to load the lecture material one again because right there we have, I mean, means and ways by which you can reach the team.
Okay, can okay.
Yeah. So it's just acting a little bit slow, but it will soon be
Mm,
up. Okay. So I think when you just look into the first material, it's right there.
okay,
Let me go up. Let me go down a bit. Okay. So
okay.
right here. Okay. Under the profile, there are various
Okay, okay,
ways in which you can
okay.
reach. Okay, my email is also there. I mean,
Oh, fine.
Facebook,
That's good.
LinkedIn, any
Okay,
other approach. And then also we indicated here how you can get the training materials and a lot more.
that's fine.
Okay,
Thank you.
all right,
Oh,
sure.
oh, that's fine. Thank you.
Okay, so please, any other question? So we address them and then. And I believe it's not just questions to also have, I mean, some sort of evaluation. Maybe there are some things you think probably we could have included, some items that you are thinking that okay maybe would have been more beneficial if we added those ones on. You can also communicate. But if you want to talk to the entire team, you have to come up here to where the podium is, where Adam is standing, and you get to talk to all of us. Yes, Adam, go ahead.
Yeah, yeah, I was thinking of you including classes, like classes in Python.
Yes. So that was one area we were supposed to look at. Now, the reason why I didn't bring that on board was because when you look at the lecture 2, lecture 3, they're already so packed, right? And also, as a very beginner level, I mean, it's one of the interesting places to bring on board or to introduce. But then mostly the struggle in there within the 2 hour scope is that you might struggle to make people understand okay when we say there's an object right there's the in sort of the properties of that object and then you talk of say inheritance. I mean, even though it's quite easy to think of it from a human perspective that okay humans have this trait and then there's how they inherit certain objects based on that and that, but sometimes it's difficult also in a beginner class to explain that within the scope of time we were given. That's why we took that out. Yeah.
Okay.
All right. Yes. So please, if yeah, Mr. Francis, you can click where Adam came to stand. Just click on that megaphone and it will bring you there. Just double click it and then it will bring you there. Okay. Are you Just a minute. Let me just give you the go ahead from here. Okay. All right. So yeah, Francis, you can go ahead. We can hear you now. You can just unmute and talk. We'll be able to hear you. Hello, Francis. Yes, kindly unmute and then let us hear you. Hello, Francis. All right, or maybe you can type it in the chat. Okay. All right. So please, any other um, views? If you want to say something, there's a megaphone in front. Just double click on it and then it will move you there. Gloria, I think we can hear you. You need to be on the megaphone first. Yes. Uh-huh. That's okay.
Okay. Mine is not a question, but just an appreciation of what was taught today about the Senpai. Most of the times when I want to do something related to exponentials and the rest, I import math before I'm able to do that. But with this, it makes everything simpler.
Oh,
So
okay.
thank you for that.
All right. Sure. You're welcome. And I hope that I mean we'll be seeing some applications of what you've gained here in the nearest future. Yeah. All right, Melvin, please, you can unmute and then let us hear you.
Okay, look, I'd like to thank you and One Quantum Ghana for giving us this opportunity to, learn and then